Today we're going to look at projectile motion. This follows straight after the equations of motion, and it's really important that you're comfortable with using the equations of motion if we're going to move on to projectile motion. These use exactly the same equations that we're going to use in the calculations here, so you need to be confident with using these in one plane, because we're going to start to get a little bit more complicated when we use them to describe projectiles. A projectile is an object which has just been kicked, fired, chucked, catapulted, flicked, in some way projected into the air. As such, it's travelling at an angle or horizontal to the ground, but it isn't on the ground. This is quite different from some other things which might be flying through the air. It needs to have been kicked, chucked, given some sort of impulse or propulsion into the air, but just an initial one. To give you a counter-example, let's look at some items that aren't projectiles. None of these are projectiles. The forces that are acting on these are more complicated, and they cause flight. These objects are flying. They're not projectiles, and we can't predict their behaviour and a simple path that they will follow due to the fact that they can control the direction they're going to travel in whilst they're in the air. These aren't projectiles. Okay, some terminology that we need to get familiar with. If we kick or chuck, project something, a projectile in the air, it's going to follow a path very similar to these lines shown here. The path that it follows, we call its trajectory. So if we trace out the route of its movement over the whole of its journey, we call that its trajectory. Now, this predictable symmetric curve has a special mathematical name, and that is a parabolic curve. So we'd want to describe it as parabolic, the curve that it follows, and it's a mathematically predictable pattern, so that's the name that we give it. It's a parabola, or we say that it's parabolic. When we do project a projectile, it flies through the air and eventually comes back down to the ground. The distance that it travels from where it was projected to where it lands is called its range, and it's different for different angles. In the models that we're going to assume where we have no air resistance, the greatest range occurs at 45 degrees. If we launched our projectile straight up, it would go really high, but wouldn't go any distance at all. It would have no range. And if we tried to shoot it straight along the ground, then obviously it's not going to spend much time in the air. So the best for getting it to go really far is a middle ground between these two. That's at 45 degrees. In this section, I'm going to go over why a projectile follows that curved trajectory that we saw before, that parabolic curve. You don't have to go through with this bit. If you're here just to look at how the calculations are done, feel free to skip ahead. But I think the understanding of why a projectile would follow a curved shape is really fundamental in our understanding of what's happening here. So why does anything happen? Forces. Forces are going to define the motion of this ball, and so we need to look at the forces acting on this ball after it's been kicked. Think to yourself for a second. After this ball has been kicked, what forces are acting on it? So not at the moment that it's being kicked, the moment after it has been kicked, what forces are acting on it? The answer is quite simple. If we assume this fact that's up here in the top right, there is no air resistance, which we need to do to simplify these problems to make them predictable, there's only one force acting on the ball. That's its weight. This ball has mass, and so it's attracted to the Earth, which also has a lot of mass. And we call that force the object's weight. Because the forces on this ball are unbalanced, it's going to accelerate downwards. Its speed at all times is going to increase in this direction until other forces come in to support it. And it's going to accelerate at what we'll assume is 10 meters per second squared. Now what on earth does that mean? That means every 1 second, its speed in this direction, its speed down, will increase by 10 meters per second. So every second, the speed of this object will increase downwards by 10 meters per second. Right. Let's look at a parabola that a projectile might follow. This is the sort of curve you will have seen balls or projectiles, when you've seen them thrown, they will follow. We need to discuss little bits of this journey to try and explain why it follows this curved path. What I'm I'm going to do is I'm going to break down its journey into equal time chunks, and we're going to see how its motion is changing in these different time chunks. So, first off, I'm going to draw one line on to try and simplify this, and we're going to do it in a set of different equal time chunks to try and simplify this journey so we can explain it in a few simple chunks. So this is the initial direction that the ball was kicked in. If I asked you to describe the direction this arrow was travelling in, you'd say, well, it's travelling to the right and it's travelling up. It's as simple as that. And we can break this motion, the motion that it travels into what we call its components that we saw in vectors and scalars video. So it has a horizontal component, right, and a vertical component, up. Right, now let's compare this with the next section of the journey. So I'm going to go for an equal time chunk, and we're going to see how its horizontal and its vertical component have changed. Now, the ball has changed direction, and if we look at its horizontal and vertical component, there's a marked difference. Well, certainly in one of the components. If we looked at the horizontal component, it stayed exactly the same. There's no difference there. But the big change that's happened here is this. The vertical component of its motion has reduced hugely. As such, the resultant vector that it's travelling in is pointing in a very different direction, because this direction, this arrow, is defined by how big this arrow is and how big this arrow is. How much to the right is it going and how much up is it going? And in this chunk of time, it's travelling far less up, but the same amount to the right. Now, why is it travelling less up in this amount of time? In essence, why is it travelling less quickly up? Well, we discussed that answer already. And that's due to the only force that is acting on it. It's accelerating downwards. Its speed is increasing downwards. It happens to already be travelling upwards, so it appears that its speed is reducing. Its speed is reducing, but its velocity downwards is getting faster. So let's continue its journey. We can see that the angle is changing yet again, and the horizontal motion doesn't appear to be changing, and the vertical motion is getting smaller and smaller until it reaches the top. And at the top, it's just travelling to the right. There is no vertical component to its motion at all. If you looked at just its up and down, it would appear not to be moving at all, and it has to do that to change direction. It's changing direction, so its velocity in that direction is zero. And then we get a symmetric pattern doing the opposite of what we saw the other time. So its vertical velocity downwards is increasing, so its speed downwards is increasing. And due to this force causing it to accelerate, it keeps getting faster and faster downwards in the same amounts that it was on the way up. The way it was reducing, it's now increasing by the same amounts each second. And we get this symmetric, predictable curve. This is all due to the fact that its weight, Earth pulling on it, is changing its velocity downwards. Due to the fact that there's no air resistance, its velocity horizontally isn't changing. There are no forces to the left, and there are no forces to the right. As such, there's no acceleration. The only change in velocity is vertically. As such, the resultant velocity that it travels in is changing direction, because these are changing in proportion to each other. Okay, hopefully that gives you an idea of why we get this curve. It's also important for when we look at separating horizontal and vertical motion in the calculations we do later on. Right, from what we just discussed, this fact should be evident. How fast you're travelling sideways doesn't affect how fast you will fall, unless you've got wings, and that's where we start to talk about those things that weren't projectiles. Things where there are other forces, like lift, for example, that are affecting the motion of the thing that's in the air. For projectiles, we're not assuming this, so how fast something's travelling sideways does not affect how fast it falls. Now, this video will be linked under the video. It's worth going to have a look at this and seeing this demonstration in action. It shows that if you drop something and shoot something sideways, they'll reach a point where they meet here. That's due to the fact that how fast it falls downwards isn't affected by the fact that it's moving to the side. Subsequently, if we want to work out how much time it's going to take to get here, we don't need to take into account the fact that it's travelling to the side. We could just assume that it was an object which was falling. If you haven't seen this video, go and have a look at it now. I'm going to move on, assuming that we have. Okay, here's another image that proves a very similar thing. This apparatus was set up to knock this ball off sideways at the same time that this one dropped. And it used a stroboscope, so it flashed a light to take lots of different photographs of them as they fell at exactly the same time. Now, what we can see is that the vertical motion is unaffected by the fact that it's travelling sideways. So I ask this question: which of these balls will reach the ground first? The answer is clear. They're going to hit the ground at the same time. Even though this one has travelled further, it's given some horizontal motion, an initial velocity horizontally, but that doesn't affect how fast it's dropping. That's really useful for us if we want to work out how long it's going to take this ball to hit the ground, because we can calculate it just as though it was this one, just as though it was dropping down. And that really simplifies things for us, and that means that we can predict its motion quite easily, actually. So they both fall at the same rate towards the ground. This allows us to treat horizontal and vertical motion completely independently. If we want to work out how long something will take to hit the ground, we can assume that it is just falling. If we want to work out how long it will take to travel a certain distance horizontally, it's the same as just an object travelling horizontally, and we don't need to worry about the fact that it's dropping. All of these events occur at the same time, so when we work out time, they'll often have a common time that things will occur at. But in terms of how far it's going to travel this way, it's not affected by how quickly it's moving in this direction. So let's look at this on a graph and talk about some of the equations that we're going to be using. This is the sort of curve that we should now be familiar with, this parabolic curve, and this is something that would have been projected, kicked horizontally from, say, a cliff face or somewhere already in an elevated position, and it drops to ground in this curve. Now let's cut up its horizontal and its vertical motion and see what's happening. Right, here are equal timestamps, how far it's travelled horizontally at different amounts of time. We're going to track this as an object just moving horizontally. You can see that it moves the same distance for each time chunk. It's not travelling any further, which means it's travelling at constant speed. Subsequently, we can use really simple equations to try and define this. This is displacement is equal to velocity times by time. So for horizontal motion, we're only going to be using equations like this, quite simple ones, because it's not accelerating, so we don't need a term for acceleration in these equations. For the vertical motion, if we look at this now, to model its vertical motion, we can just assume that we drop the ball. And we can see here that the distance it's travelling for each time chunk is getting bigger and bigger. That's because it is accelerating. So we're going to have to use the equations of motion that we looked at in the last video. Things like s equals ut plus half at squared, v squared is u squared plus 2as. The four equations that we know that are on our exam booklet that we can go to and use. You don't need to be able to memorise them. Yet again, I just want to make it really clear that we're ignoring air resistance. That's why this isn't changing. In reality, there would be a slight difference. This would slow down a little bit due to the air that's getting in its way. But that complicates things in a way that we wouldn't be able to calculate in this simple manner. This is a great model for stuff that's happening, and is a really important tool for us to learn. So here are the equations that you will get on the exam sheet, and you find them right here. You don't need to worry about remembering them. So we're going to use these whenever we're working out the vertical motion of a projectile. For the horizontal, we just need to know that speed is equal to distance divided by time. Right, we're going to have a look at an example here. Have a quick read of the question and pause the video and give it a go. We'll then go over the question in a second and you can see whether or not you've gone about it the right way or the wrong way. Right, here's the problem at the top. Let's go over how to work it out. A darts player stands 3 metres from the board. The dart leaves her hand horizontally and it takes 0.2 seconds to reach the board. Calculate the initial velocity of the dart and the vertical height that the dart falls. So I'm going to draw a bad diagram here. We've got a dart. Let's put some flights on it. Lovely. And it's going to hit a darts board over here. Terrible. and it takes 0.2 seconds, and it's 3 metres away. So this distance from here to here is 3 metres. Now, the horizontal line between the dart and the board is this. But we know it's not going to travel on that sort of trajectory. It's going to follow this parabolic curve down here somewhere. We don't know what that distance is. Sorry, that's a bad curve. There we go. It's going to hit the board somewhere down here, and the second part wants us to work out what is this vertical distance. Ooh, let's draw that a bit better. From here to here, how far is it going to fall? The first thing it's just asked us is what is the initial velocity of the dart. So, part A. We know that it has travelled 3 metres. It was projected horizontally. It leaves her hand horizontally. This is important. So the initial velocity has no vertical component. It travels 3 metres in 0.2 seconds. All we need here is that velocity, we'll go for u because this is initial velocity, is equal to displacement divided by time. So it travels 3 metres in 0.2 seconds, and that gives us a speed of 15 metres per second. Simple. Now the vertical motion is a little bit more tricky due to the fact that it's accelerated. So part B. We want to know how far it's gone down here, which means we're using one of the equations of motion. So first step for any equation of motion is to write out SUVAT. So S is the displacement. That's what we're trying to work out. Now we're working vertically here. This is only vertical motion. As we said before, the fact that it's travelling horizontally doesn't affect how quickly it falls. So we can assume we are just dropping this dart. So the displacement, we don't know it. It's our question mark. U is the initial velocity. It left her hand horizontally. So the vertical initial velocity is 0 metres per second. It's not travelling with any speed at the very beginning downwards. It's not started to accelerate due to its weight yet. The final velocity we don't know, but it's not what we've been asked to calculate. So I'm going to put a cross next to it. I don't need to know it. Acceleration is the acceleration due to gravity. And we're always going to use this same value, unless you're given another one, maybe it's on a different planet, for example, and we use 10 metres per second squared. And the time, well, we knew it took 0.2 seconds to hit the board, so this is how far it must have fallen in that amount of time. As I said before, they've often got a common time, so 0.2 seconds to hit the board. Right, so we select the equation by looking for the equation that doesn't have the thing with the x next to it, so the thing that doesn't have v in it, and that is s equals ut plus a half at squared. So the displacement is equal to 0 times by 0.2, so that's just going to be 0, plus 0.5 times by 10 times by 0.2 squared. So that's equal to 0 plus 5 times by 0.04, and that is going to be equal to 0.2 metres. Okay, so we completed the question. We used horizontal motion, uniform horizontal motion, not accelerating, so we just used speed equals distance divided by time to work out how fast it was travelling. Then as it was accelerating downwards, we just assumed that our dart was dropping. If I draw this out, this is our dart at the beginning, and it's travelling just horizontally. It then starts to drop, and doesn't drop very far at the beginning. It's accelerating, and it gets further, and further. It's accelerating, and we can assume that it is just dropping. This motion was just the dart dropping down. We weren't taking account of the fact that it was travelling to the right to work this out. It was the same as if we just said, I'm dropping a dart. After 0.2 seconds, how far will it have gone? At that point, it had hit the dartboard, so it wasn't going to go any further. How far did it travel in 0.2 seconds? And we plugged that all in, and we worked out that it would travel 0.2 metres in that amount of time. Here is another example. I've got an A, B and a C, And the last part is going to be a little bit more involved. It's going to bring together our skills at looking at combining vectors to get a resultant vector. So this last question is going to be quite involved. What I want you to do for a second now is just pause the video and have a go at this question yourself. Right, let's give this a go. Part A and B should be very familiar. If you're okay with the dart question, you should be fine with this. A ball is thrown horizontally from a cliff with an initial velocity of 3 meters per second. So it was thrown horizontally again. It landed 9 meters away. How long did it take for it to land? So it travelled at 3 meters per second this way until it eventually hit the ground. So it can't travel any further horizontally because it's hit the ground. But we know it travelled 9 meters this way at 3 meters per second. So yet again, we've got quite simple equations just for horizontal motion. We know that velocity, its initial velocity, is equal to the displacement divided by the time. We want to know how long it took to hit the ground, so we want time. So if we rearrange that, time is equal to the displacement divided by the velocity. So it travelled 9 meters at 3 meters per second. That means that it took 3 seconds. 9 divided by 3, 3 seconds at 3 meters per second. It's as simple as that. Speed is distance divided by time. Time is distance divided by speed. 9 meters divided by 3 meters per second means it took 3 seconds to travel that far. B wants to know how high the cliff is. We know that the flight lasted 3 seconds. We now need to take account of vertical motion. That means it's going to be accelerating, which means we need to use SUVAT again. So S, U, V, A, and T. The displacement is the thing that we want to know. We don't know it yet. The initial velocity. Because we're assuming it's falling, it's being dropped. We don't need to take account of this horizontal motion anymore. We can just look at this diagram here on this side. We don't need to consider any of this over here. Doesn't concern us. It's just dropping. So if we're just dropping it, its initial velocity is going to be 0 meters per second. Its final velocity, we don't know, but we also don't need to calculate it yet. So I'll put a cross through that one. Its acceleration, yet again, is 10 meters per second squared. And the time that it took to get there, we just found, was 3 seconds. So the equation which doesn't have the v in it, the one that we used before, S equals ut plus a half at squared. Now in this example we don't need to do any rearranging, but if we did, it's really important, or it's easier if you put all the numbers in first. As it happens, it's rearranged the correct way for us. S is the subject of the equation, so we can just plug the numbers straight in. So ut is 0 plus 0.5 times by 10 times by 3 squared. So that's equal to 5 times by 9. So that's equal to 45 meters. In essence, in this question again, it's just asked us, in 3 seconds, under the acceleration due to gravity when dropped, how far did it travel? And it travels 45 meters. So it must be 45 meters from here to the bottom of the cliff if it took 3 seconds to hit the ground. Okay, part C. This gets a little bit more complicated. It says, what is the velocity just before hitting the ground? Now, it hasn't stated vertical velocity, for example. It wants to know its velocity in the direction it's travelling. So before it hits the ground, it's travelling in this direction, roughly. It wants to know what is its velocity in this direction. So we're going to have to work out its different components of its velocity. We're going to have to work out how fast is it travelling to the side, and how fast is it travelling down. Because when it hits the ground, it's travelling right and down. We need to know how much right, how much down. Then we can use Pythagoras to work out how much right and down, and at what direction it's travelling. So let's start with the horizontal motion. This one's simple. There's no air resistance, so there's no resultant force acting on the object, so it doesn't slow down. So when it gets to the bottom, it's still travelling at 3 meters per second. We assumed that in the first answer in A. So its velocity, its final velocity horizontally, is equal to 3 meters per second. Now we need to work out the final velocity vertically. We're going to need to use suvat again for that one. So let's write this out. Do we know which distance it's travelled? Yes, it travelled 45 metres, we just worked that out. Its initial velocity was 0. Its final velocity we want to know. Its acceleration is 10 metres per second squared. And its time that it took to get there was 3 seconds. I'm going to give this the subscript v, vertical velocity, its final velocity vertically, and this was its final velocity horizontally. Now we know all of the other variables. If that's the case, we can use any of the equations that we want. Now it's simplest to use an equation where v is already the subject of the equation. So v equals u plus at is the simplest equation for us to use here. So that's equal to 0 plus 10 times by 3. So it's going to be travelling vertically at 30 metres per second. Right, let's draw this on a quite simple diagram here. It's travelling downwards. Its VV was 30 metres per second. And it's travelling to the right at 3 metres per second. So its resultant velocity from these two vectors added together is going down and to the right. And we need to work out this resultant that I'll call r. Going back to our scalars and vectors video, we know that we can add these two vectors together using Pythagoras, which told us that the two small sides of a triangle A and B equal, when squared and added together, equal the square of the large side of the triangle. A squared plus B squared equals C squared. So r is our C here, and 30 and 3 are A and B. So 3 squared plus 30 squared equals r squared. So r is going to equal the square root of 3 squared plus 30 squared. The solution to 3 squared plus 30 squared is equal to 30.14 metres per second. So that's the resultant vector of it travelling 30 metres per second vertically downwards and 3 metres per second horizontally to the right. So along this line it's travelling at 30.14 metres per second. Now, it asks for a velocity. As we know from vectors and scalars, velocity is a vector, which means it has a magnitude and a direction. We've got the magnitude. We know the size of its speed. We don't know what direction it's travelling in yet. So we need to work out a direction, and we're going to do that as an angle relative to either vertical or horizontal. I'm going to go for the angle from the horizontal surface, from the ground. So if you were stood on the ground down here, what is the angle from the flat surface in front of you to where this ball is landing? So we're going to go for this here, and I'll mark that with this theta here, that's meaning the angle. So here we need to use trigonometry to work out what this angle must be. We know all three sides of our triangle. We'll always know with these things the horizontal and the vertical, so the two short sides. So we're going to use tan in almost all of these examples. So tan theta, we know from SOHCAHTOA, so TOA equals O divided by A, the opposite divided by the adjacent. So that's equal to 30 divided by 3, which is 10. So I know that tan theta equals 10, and I need to work out this angle. To do that, we do the inverse tan function. So to move this from this side to that one, we keep the theta on this side, and that equals tan minus 1. You'll find that function on your calculator of 10. And if you use your calculator to work this out, you won't be able to work this out in your head. You would get an angle of 84.3 degrees from the horizontal surface. 84.3 degrees from horizontal down here. So it's coming down almost vertically. It's very close to 90. It's coming down very, very steeply. So now we've worked out the resultant velocity of these two velocities, giving us a magnitude, the scalar, and the direction that it's travelling in, 84.3 degrees from this horizontal surface. So that gives us a vector, 30.14 metres per second at 84.3 degrees from the horizontal. So we've completed this problem. It's a tricky one and puts together all of the skills we learnt in the previous 2 videos. Could you do it? Right. Next, what I want you to do is you'll find these questions linked in this presentation underneath the video. I want you to go away and have a go at these 3 problems yourself. If you get stuck, come back to the video and watch how we did some of the trickier problems, and then go back and try and get these done yourself.